Electricity generation by combustion of fossil fuels or nuclear power or renewable energy sources like wind or hydroelectric power involves generators. They generate electricity by electromagnetic induction. But solar energy does not involve generators. Solar panels convert light energy into electrical energy directly.
Electricity generation usually requires electric generators, but it's not required for solar panels. It's amazing.
Hi, Tissue. Is that a solar-powered torch?
You are here at the right time. Now we know the factors affecting the efficiency of solar panels. I wonder how people discovered that light energy can be converted to electrical energy.
It's all thanks to him.
Albert Einstein? I know about his theory of relativity. How is it related to solar panels?
Einstein didn't study solar panels directly, but in the early 20th century, he studied the photoelectric effect. Apart from the properties of waves, he found that light has the properties of particles. When light interacts with atoms, it behaves like a particle. The photoelectric effect led to the concept of photons. It is important to the later research of solar panels.
Wait, Dr. Tong, what's the photoelectric effect? What's a photon?
A photon is a particle. It is a particle of light. Light behaves as waves as well as particles. In 1905, Einstein published several papers. One of them is about the photoelectric effect. He got the Nobel Prize in Physics in 1921 because of this work. Can we do some experiments to know more about the photoelectric effect?
Sure, let's do it.
The photoelectric effect is a physical phenomenon. When light with a suitable frequency falls onto a metal surface, electrons will be emitted. We cannot see it with our eyes, but we can illustrate the effect with this apparatus.
What is it? Why is there a piece of foil inside?
That is a piece of gold foil. This is a gold leaf electroscope. It can detect static electricity. I rub the acrylic ruler for a short while, and now the ruler carries some net charges. When I place it near the electroscope, what do you see?
The gold leaf rises. Why is that?
The ruler carries net charges. Charges are induced on the metal plate and the gold leaf. Since the metal plate and the gold leaf carry like charges, they repel each other, and so the gold leaf rises. You may touch the electrode.
The gold leaf falls.
Your body is an electrical conductor. You can conduct electricity. Your body removed the net charges. That is why the gold leaf falls.
How is it related to the photoelectric effect? Dr. Tong, shall I light it up with a torch?
Yes, we are going to do it, but we need one more thing.
What's that?
We need a zinc plate. The setup is charged up already. The gold leaf has risen. Try to illuminate it and see what happens.
Nothing happened. The light must be too weak.
You may try the spotlight. It's way more powerful. Try it.
It should work now. No, it doesn't.
Nothing happens, even with such a high power. Let's try an infrared lamp. It doesn't work either. Let's try an ultraviolet lamp. Before that, we should put on safety goggles. Does it work?
Nothing happens.
The radiation emitted by this ultraviolet lamp is UVA. We can try another UV lamp that is used for sterilization. The radiation it emits is UVC, which has a shorter wavelength, but a higher frequency.
The gold leaf falls. Why is that?
Einstein tells us that when light interacts with matter, we can treat light as particles. Light particles carry energy. We call them photons. Why does the photoelectric effect occur? When exposed to photons with suitable frequency or energy, some electrons on the metal surface, such as the surface of this zinc plate, are removed. Electrons carry negative charges. The gold leaf falls as the negative charges are removed.
Why are the electrons removed by UVC only?
This is related to the frequency or energy of photons. The energy carried by one photon is proportional to its frequency. The higher the frequency, the higher the energy of the photon. We have tried different radiations. The frequencies of visible light and infrared radiation are lower, so the photons do not have enough energy to remove the electrons. The frequency of UVA is a bit higher, but the photon energy is still not high enough. UVC has the highest frequency. The photons have enough energy to remove electrons from the zinc plate. The photoelectric effect takes place.
Provided the photon energy is high enough, the photoelectric effect occurs. If the photon energy is not sufficient, it doesn't occur no matter how strong the light is.
Exactly. Photon energy is related to frequency. The higher the frequency, the higher the photon energy. A century ago, many scientists were puzzled by this phenomenon. Einstein introduced the concept of photons and solved this problem. He eventually got the Nobel Prize.
How can we carry out an experiment of the photoelectric effect?
The experiment of the photoelectric effect is quite complicated. I'll first simplify the experiment with a computer simulator. You may visit this website to access the simulator. You may also do it at home.
Do these wave packets represent light?
Yes, they are the photons. The wave packets fall onto the surface one by one, representing the incidence of photons.
When the photons come into contact with the silvery thing, I see blue dots coming out. What are they?
The silvery surface represents the metal surface. Upon incidence of photons, some electrons are emitted from the surface. The blue dots represent electrons. As they are produced by the photoelectric effect, they are called photoelectrons. Each wave packet represents one single photon. It can only remove one electron.
What if there are more photons?
We can adjust the irradiation intensity to adjust the amount of light.
When there are more photons, more photoelectrons come out.
Let's lower the irradiation intensity. Then, we try to adjust the frequency of light, while keeping the intensity unchanged. Let's see what will happen.
Why are there no photoelectrons?
Photon energy depends on frequency. When we decrease the frequency, photon energy decreases. When photon energy is lower than a certain level, it cannot remove any electron from the metal.
I noticed that when you adjusted the frequency until the value of EV is lower than that of zinc, there were no more photoelectrons. What is the relationship between them?
EV is a unit of energy called an electron volt. 1 EV is equivalent to 1.60 times 10 to the minus 19 joules. We can see the value of EV for zinc. The value is 3.74 EV. This is called the work function of zinc. What is the work function? It is the minimum value of photon energy required for the photoelectric effect to occur. If the photon energy is lower than the work function, the photoelectric effect will not occur. Therefore, when I adjusted the photon energy below the work function, the photoelectric effect didn't take place.
Is the work function different among metals?
Yes, indeed. It depends on the ability of metal ions to bind the electrons. Some metals may have stronger binding. Their work function is higher. Some metals may have weaker binding. Their work function is lower.
When the photon energy is decreased, the photoelectrons move slower. Why is that?
You've made a good observation. When photons are incident on the metal surface, some energy is used for the electron to escape from the metal surface. This is the work function. Other than the energy used for the work function, the remaining energy becomes the kinetic energy of the photoelectron. You can see that when the photon has a higher energy, after using part of the energy for the work function, the photoelectron will get a higher kinetic energy, so it moves faster. If the photon energy is lower, the kinetic energy it gives to the photoelectron is lower, so it moves slower.
What are the two grey things?
The sign MA represents an ammeter, which measures the current. The unit is milliamperes. The one with the unit of volts measures the voltage. It is a voltmeter. In this experiment, at the opposite of the metal plate, there is another metal plate, which is called the collector. a voltage is applied between the metal plate and the collector. The voltage produces an electric field. The electric field can accelerate or decelerate the photoelectrons. If the voltage is positive, the photoelectrons are accelerated. If the voltage is negative, the photoelectrons are decelerated. The voltage can be adjusted. The number of electrons reaching the collector electrode, that is, the current, is measured by the ammeter. The result is shown in this graph. The current is on the y-axis, while the voltage is on the x-axis. You may adjust the voltage between the metal plate and the collector from positive to negative values. Let's see how the current changes.
Okay. The current drops gradually.
Yes.
It stops eventually.
Yes, the voltage is slowly decreased. When it becomes negative, the electrons are decelerated. When the voltage reaches a certain negative value, the speed of the photoelectrons just becomes 0. They cannot reach the collector. The current becomes 0. The voltage that just stops all the photoelectrons is called stopping potential. Now we try another thing. We try to change the irradiation intensity by increasing it. Then we will repeat the experiment. The voltage will be decreased gradually. Let's see what will happen. We increase the intensity first. We adjust it to 10, which is the maximum. You may now decrease the voltage between the metal plate and the collector.
Let's see what we get. It drops very fast, but it stops at the same value.
The voltage was initially positive. The electrons were being accelerated. As the irradiation intensity increases, more electrons reach the collector. The current is larger. You can see that the current is larger at the beginning. When the voltage is decreased, it eventually becomes negative and reaches the stopping potential, making the current drop to 0. It implies that the stopping potential is independent of the irradiation intensity. No matter how intense the light is, when the stopping potential is reached, the current becomes 0. We will do the experiment in another way. We changed the irradiation intensity before. Now, we keep the intensity constant and change the frequency of photons. The photon energy is now reduced to 3.99 eV. The frequency also decreases. Let's repeat the experiment. We adjust the voltage from positive to negative values slowly. Check out the change in the current.
The stopping potential is now different.
Yes, the absolute value of the stopping potential is smaller. It is closer to 0. The explanation is simple. When photon energy is lower, the kinetic energy of photoelectrons is also lower. For a lower kinetic energy, a smaller stopping potential is sufficient to stop the photoelectrons from moving. As a result, stopping potential only depends on the frequency or energy of photons, but not the irradiation intensity.
How about the experiment? When and where shall we do it?
Be patient. Before the experiment, let's look at the equations first. Photon energy depends on frequency. The photon energy is given by E equals hf.
I know that F stands for frequency, but what is H?
H is the Planck constant. It is one of the fundamental constants in nature. The value of it is about 6.63 times 10 to the minus 34 joules second. The product of the Planck constant H and frequency F is the photon energy E. As mentioned, when photons fall onto a metal surface, electrons are removed from the metal surface. The minimum energy required is the work function. Some of the photon energy is used to overcome the work function. Therefore, the photon energy HF minus the work function, which is denoted as W, gives the remaining energy that becomes the kinetic energy of the photoelectron. The maximum kinetic energy is denoted by EK. The equation hence becomes EK equals HF minus W. As mentioned, there is an applied voltage between the metal plate and the collector. The photoelectrons can be accelerated or decelerated. When the voltage becomes negative and reaches a certain value, the photoelectrons are stopped and cannot reach the collector. This is the stopping potential. We call the absolute value of stopping potential V0. Note that the symbol V0 is defined by a positive value. The energy change for an electron in moving from the metal plate to the collector is EV0. If this energy difference just equals the maximum kinetic energy of the photoelectrons, no photoelectron can reach the collector. So, the maximum kinetic energy is given by EK equals EV0. Combining the two equations, which are EK equals HF minus W and EK equals EV0, we finally obtain EV0 equals HF minus W.
Shall we start the experiment now? What do we do with the apparatus?
Let me introduce the apparatus first. Let me switch on the mercury lamp. The blue light you see is the light emitted by the excitation of mercury. The light consists of different frequency components, but we will only use 4 of the frequencies. The equivalent wavelengths to these frequencies are 546 nanometers, 435 nanometers, 404 nanometers, and 365 nanometers. You will see the change in the number when I adjust the monochromator. The number shows the wavelength of light allowed to pass through the monochromator. There is a cesium plate inside this apparatus. Photoelectrons are produced upon the incidence of photons. The voltage between the metal plate and the collector is adjusted by the computer. The computer can record the data while adjusting the voltage. When the voltage reaches a certain negative value, which is the stopping potential, at that point the current becomes 0. No photoelectron can pass through. Do you remember the equation of the photoelectric effect we mentioned before?
I have forgotten.
Never mind. Let me remind you. The equation is EV0 equals HF minus W. V0 is the absolute value of the stopping potential. H is the Planck constant, F is the frequency. W is the work function. When the entire equation is divided by E, it becomes V0 equals HF over E minus W over E. We can plot a graph of V0 against F. V0 is on the y-axis, while F is on the x-axis. We plot the stopping potentials against the corresponding frequencies on the graph. A straight line should be obtained. The slope of the graph is h over e. Multiplying the slope by the electron charge e, we can get the experimental value of the Planck constant h. The y-intercept shows the work function. The value of w over e is still the work function, just that the unit is different. It is given in eV.
How is the photoelectric effect related to our daily life?
It is a very important discovery. Einstein discovered the photoelectric effect a century ago. It tells us that light has the properties of waves as well as the properties of particles. After that, scientists found that every kind of particle has the properties of waves. This is a fundamental idea of quantum mechanics. Quantum physics has become an important branch of physics.
Quantum physics? I've heard of quantum computers and quantum communication. Are they the same?
All the particle motions in the microscopic world have to be described by quantum mechanics. They include atoms and atomic nuclei. It is the foundation of modern technology. Quantum computers and quantum communication are all based on quantum physics.
I've learnt a lot about the photoelectric effect, but I still don't understand how solar panels generate electricity. It doesn't look like metal at all. Does it generate power differently?
Solar panels do not use the photoelectric effect, but the photovoltaic effect.
What is the difference between them?
What are these made of?
I still remember silicon, 3 types of silicon.
Yes, it is silicon. It is an important element in semiconductor technology. Solar panels are made of silicon. Electrons are produced when exposed to sunlight. It is similar to the photoelectric effect we have just learned. The photoelectric effect occurs in metal, but the photovoltaic effect occurs when a semiconductor is exposed to sunlight. Electrons and hence the current are produced. The major ingredient of these solar panels is silicon, but tiny amounts of the atoms of other elements are added. According to impurities added, silicon can be categorized into p-type and n-type.
P-type and N-type. What's the difference?
Free electrons are readily produced in n-type silicon. On the other hand, holes are readily produced when energy is given to p-type silicon. Holes are the empty electron sites in atoms. Some atoms may lose electrons. Since electrons carry negative charges, the atoms that have lost electrons become positively charged. So the holes behave like positively charged particles. They are free to move among atoms and behave like positively charged particles. You can imagine. There are more free electrons moving inside the n-type semiconductor and more holes moving inside the p-type semiconductor. A solar panel has both p-type and n-type semiconductors. The 2 types of silicon are joined together. The place where they connect is called a p-n junction. When sunlight is incident upon the p-n junction, both the electrons and holes are produced in the junction. Electrons are negatively charged while holes are positively charged. Electrons migrate towards the n-type semiconductor. Holes migrate towards the p-type semiconductor. When the solar panel is connected to an external circuit, such as a light bulb, the electrons will move from the n-type semiconductor to the light bulb through the wire. The light bulb lights up. Finally, the electrons return to the p-type semiconductor and integrate with the holes. The charges are neutralized. The process repeats. The solar panel keeps on generating current and lights up the bulb.
Where there's sunlight, there's electricity.
We should also notice that in the photovoltaic effect, the photon energy required for solar panels to generate electricity is lower. The frequency required is also lower. But for photoelectric effect, we need ultraviolet radiation to be shone on the metal surface. Only UVC is powerful enough to make it happen. The frequency and photon energy required are higher.
Yes, solar panels seem more practical to use.
The development of semiconductor technology is flourishing. Using new technology, the production of solar panels becomes more efficient and less costly. Their scope of application has become wider. Many scientists are developing third-generation solar cells. The most representative examples include organic solar cells and perovskite solar cells. Let's visit a university laboratory and see what researchers are doing. Hello, Fong.
Hello, Dr. Tong.
Can you share your research with us?
Sure. We are researching on perovskite solar cells. Its production is similar to organic solar cells. Let me show you the production process of the perovskite solar cells.
Sure.
First, we mix the raw material with the solvent to make a precursor. The precursor is then coated evenly on a surface. The method we use is called spin coating. By high-speed spinning, the precursor forms a smooth coating. We can also adjust the thickness of the coating by controlling the speed of spinning. Next, the coating will be heated so that the crystalline structure changes. We can see the color of the coating changes from yellow to black. That means it acquires the ability to absorb light. Moreover, this new type of solar cells has high flexibility. They can be used on a curved surface. Their application will be broader in the future.
That is right. Even for the same material, if the crystalline structures are different, their physical properties can vary substantially. To know the crystalline structure, we need to use the GWAX machine behind us. How does it work? When light passes through a grating, fringes are formed due to the interference of light. The working principle of GWAX is similar, but not with visible light. X-ray is incident on the crystals, and fringes are formed. From the pattern of the fringes, the crystalline structure can be deduced.
That's right. Let's look at these figures. During the production process of the perovskite solar cells, it changes from yellow to black. In fact, the crystalline structure of the yellow one is shown by the figure on the left. It is yellow and incapable of absorbing light. The figure on the right shows the structure of the black one, which is after heating. It is effective in absorbing light as well as conducting electricity. In our research, apart from the initial and final states, we are interested in how it changes from the initial state to the final state. By understanding the process, we can try to control it and make the transformation more intact and ordered.
As yet, the stability of perovskite solar cells is still much lower than that of traditional crystalline silicon solar cells. More talent and time are needed to improve the solar cells, thereby promoting wider use of them. As the demand for new energy grows, there is huge room for development. If you are interested in this industry, you may consider working on the research of solar cells and making contributions to the development of new energy.